In this video, we're going to learn what it means to design a visual wake words model. Now, before we do that, let's take a step back and look at where we are. We talked a little bit about collecting data and pre-processing the data from an image-based task. Now, I'm going to talk about designing a model before we jump into training the model. Why do I want to do this? I want to do this because when you look at an image classification with a task, there's a lot of different neural networks out there. This graph is showing you the variety of different models that are out there that give you the accuracy versus performance latency trade-off curve. So for example, if I take ResNet 152, I can have very high accuracy, but then I have to pay a fair bit in terms of the computational requirements because it demands over 20 giga operations to make a single forward pass. The reason I'm talking about this is that just a few years ago, there was this big challenge that we faced, which was about how do we take these big models and shrink them down so we can actually be running them efficiently, not on some big cloud computing server, but on a smart handheld device. Because if we try and run these big models on these small devices, they're going to run out of battery really fast. So I want to take you along a little bit of history in order to be able to design models that are better suited for TinyML specific tasks. So if you want to shrink models down, there are two fundamental things. You have to be able to shrink down the number of parameters that are actually inside the model. That's the size of the circle here corresponds to the number of parameters. So for example, in VGG19, there are over 155 million parameters. You want a network that is small in terms of parameters. The other thing that you want is also to make sure that it runs efficiently. You don't want it to need a lot of computation. So there are two fundamental constraints. There's a number of model parameters, and then there's the number of hardware operations you can perform per second. These two together actually give you a small network that can actually run efficiently on a mobile device or a TinyML device. So let's try and understand how do we break a complex model down so we can try and shrink things down. I've got to take you back to the fundamentals. When you look at an image-based task, you spend a lot of time doing convolutional operations. Almost all the different networks I showed you, they all use convolutions at the heart of it. So this is a slide from our part one, where we looked at applying a filter over an image on the left, and you ended up with the image on the right. What is really happening behind the scenes when you do this convolution is extremely important to understand, because this is the foundational building block that has consequences down the road. If you look at a standard convolutional operator, what you are really doing is that you've got a filter, the yellow here, and that is scanning through the original image, the input image on the left, and it's producing the corresponding blue pixel on the right is a set of pixels that you're looking at, for the left. Now, if I have a 3-channel RGB image, a 3x3x3 filter that is scanning over all those different channels at the same time and outputting a single point. To be more specific, the input feature map is 8 in width and 8 in height, and it's got 3 channels. Now, the kernel is running over it is a 3x3x3 kernel, and that's the yellow kernel that we are looking at. The output is the single orange dot that we are seeing is a kernel that's going through the image on the left. The question is this standard convolution is quite complicated. So is there some way to break down this convolution into simpler operations rather than doing one massive compound convolution? The reading that I have breaks down the math and tells you the exact number of multiplications and additions that we're going to be performing for this standard convolution. It's quite strongly dependent on the number of channels you have, the number of filters you have, and so forth. So please pay attention to the math and the reading there. The thing that I'm leading into is that we can break down this standard convolution into smaller pieces so that we have much more, we can run it much more efficiently on hardware. So that's where the depth-wise convolution comes in. The depth-wise convolution is this fundamental idea that instead of doing a convolution, like a compound convolution across all the channels, what if I took the individual channels out and I did a convolution on each channel individually. And after that, I do a point-wise convolution to fold all of those output feature maps into a single point, which is exactly where the original standard convolution would have gotten us to, right? So I'm trying to combine a depth-wise and a point-wise separable convolutions together. So instead of doing one big compound convolution, I'm taking two simpler steps, a depth-wise convolution across the individual channels, and then a point-wise convolution to produce the single output value. So if we do this, one of the key things that we get out of it is that we end up reducing the number of multiplications and additions that we do. Now, I'm not going to get into the math here. The reading does a good job of explaining this. So please pay attention to it because it's extremely important that you have an appreciation for the difference between a standard convolution and a depth-wise separable convolution, because you will see that it can dramatically cut down the amount of computations needed. And that is the fundamental step in making improvements of reducing model size and improving the latency both at the same time. So here is the ratio that you would have if you were to compare depth-wise separable convolutions to a standard convolution, just to put things in perspective. If, for example, I had 100 filters that I was applying, and I had for each of those filters, a kernel size was effectively 512 dimensions by 512 dimensions. Just to give you an example, it would be 100 times more efficient to do a depth-wise separable convolution than a standard convolution. In other words, it performs 100 times lesser multiplications. So do the math from the examples in the reading, and then you'll see why the difference is so large. And this is exactly what came out of Google a couple of years ago when few engineers sat down with their original convolutions, and they were scratching their head and saying, how can we reduce these convolutions? And voila, they said that if we could split this standard convolution up into dealing with the individual channels and then do a coupled pointwise convolution operator at the end. And that's what led to MobileNets, which is a very specific type of convolutional neural network that has taken off remarkably and is now being deployed widely across many devices because it's dramatically reduced the computational requirements as shown here. Now you can see the size of this bubble is small because it has fewer parameters inside the network and is also very much to the left, which means that it is because it requires little computation and achieves a fairly good amount of accuracy. In the recent years, of course, ML engineers have made a number of improvements over it. But the point is that it actually achieves remarkably good efficiency. And that is the state of the art, for smartphones, back in the day. And that's what we are primarily using today. So if you compare this baseline, it's still fairly large because it has 16 megabytes compared to our dinky little kilobyte amount of memory that we have in our microcontroller. We are still 64 times off. So we need to do something in order to shrink this model, which is already quite small, and make it much, much smaller. So that's where some subtle optimizations that we can do to the baseline come in. So let's talk about this equation, which is presented in greater detail in the reading. It explains the convolution is performed in two steps. The left-hand side corresponds to the depth-wise aspect of the convolution, and the right hand is doing the point-wise side of the convolution, as I mentioned earlier. The depth multiplier is used to reduce the number of channels at each layer. And so this depth multiplier corresponds to the width multiplier alpha over here. So we are combining these two steps and we have a little addition in the middle. Now, within each of these individual steps, we can play a couple of games. As you're doing with the convolution, you can control the number of channels you're looking at within each layer. By controlling that, you are effectively going to be able to control the number of different computations that you will do across the entire network. So reading has more detail, but the critical message is that you can control this parameter alpha between 0 and 1. And this has a great benefit in terms of cutting down both the size of the model as well as the computational requirements from the model. Now, this table over here shows you a variety of different pieces of data. Let me walk you through it. So the first row is showing you, the baseline model for mobile nets. It shows that it has a baseline accuracy that achieves an accuracy of 70.7% and does really well. And what's interesting though is that if I change the alpha down by scaling it down by 25%, I can drop a little bit of accuracy, but then I get a real bang for the buck in terms of the number of parameters that's actually inside of the network. By reducing the number of parameters, I'm effectively able to shrink the network down. And as you look at different values of alpha, you see that we're going to make this network quite small as long as we are willing to trade off a certain level of accuracy. In addition, you can also see that the amount of computation associated by scaling down alpha starts decreasing. And this is, again, because you are limiting the number of channels you're effectively looking at. And that's one way of controlling, this knob. Another way of controlling the knob is actually deciding how big or small the image is that we're going to be inputting. Previously, I showed you a cat image, which was 224 by 224 pixels. And then we can shrink that down even smaller to 128 by 128. Of course, we're going to take a hit on accuracy, but look at the number of max, of multiply accumulates that you have to perform. It's a remarkable drop in there. And that's huge compared to having, the same alpha. That's the critical message I'm going after here. So please keep in mind, though, that there are different kinds of optimizations. In fact, there's a whole variety of different kinds of optimization that you can perform, across the number of channels you applied, the number of filters you're applying, what alpha value is, and a whole bunch of hyperparameters you can tune. And that's effectively what's called the neural architecture search. Neural architecture search is a way of trying to find the best combinations of parameters and hyperparameters through the sea of different parameters, to achieve the smallest model that gives you the best accuracy. Now, I don't have an answer or a magic bullet that kind of tells you what the perfect type of parameter search scheme is going to be. People have come up with many different kinds of schemes, but the critical message here is this. If you want to design a model for neural networks that fit on resource-constrained devices, number one, I want you to think about, more than just the number of layers you're putting together. We need to be able to understand what the mechanics that are determining the parameter sizes. So how can I shrink the number of parameters here? And how to also make it run more efficiently by understanding the operations that are actually being used. Now, this is a bit more advanced and there's a lot more to it. And as we go into part 3, I'll try to give you a little bit more detail into these kind of things. Here, I'm trying to give you a flavor for carefully designing the models more. So just by looking at the high-level structure of the overall neural network. And there are lots of nuanced parameters we can play with. And that is key in terms of making the model smaller. And that said, in the next video, let's pick up and get ready to train the neural network.